Hello everyone, I'm Dibyadip Chatterjee. In this talk, I will be presenting a large-scale dataset we recently collected called Assembly101. In this dataset, we are looking at the toy assembly problem. These are simple, put-together types of toys with about 5 to 15 components. We are interested in multi-step activities that last over longer periods of time. Also, we want to work with non-strict sequences. That means these toys can be assembled in varying orders, maybe starting first with the chassis, or the arm, or maybe even the wheel. Assembly101 features 8 static camera views and 4 egocentric views of people assembling and disassembling these take-apart style toys. To record this dataset, we built up a disk-sized cage on which we mounted 8 RGB cameras. These provide us static views in 1080p resolution, while the head mount has 4 monochrome cameras, one on each corner. Based on this setup, we recorded 362 sequences of people assembling and disassembling these 101 take-apart toys. From all the views combined, we have over 500 hours of footage. For our dataset, we collected an extensive number of annotations, including action labels at 2 granularities, mistake labels, and skill labels. The fine level actions are defined by the interaction with 1 or 2 objects. An example of a fine action is position force wheel. The coarse actions can be considered goal-oriented, where each goal is related to a vehicle component, for example, detached bumper. We merge several of the fine-level actions into a coarse action label. For example, detached bumper is composed of 5 fine-grained actions. What's really interesting about our dataset is that we have many instances where people make assembly mistakes and then go back and correct themselves. In our dataset, mistakes could be due to different reasons, such as wrong ordering of action sequences or wrong positioning of objects. Hence, we annotate the coarse assembly segments with a parallel set of labels. These are mistake, correction, and correct labels. For extracting the 3D pose of hands, we perform hand tracking from the 4 egocentric cameras, followed by extracting the 3D key point locations. Summarizing, the annotations are collected at 5 levels of hierarchy, starting with frame level 3D hand poses, all the way up to video level skill annotations. We benchmark our dataset on 4 tasks specifically targeted at training a smart assistant. I will mainly be talking about our action recognition benchmark. Please refer to our paper to find more information and results for the other benchmarks. We define action recognition as classifying a pre-trimmed action clip into any one of the 1380 fine-grained action classes. As our baseline, we use temporal shift module, also popularly known as TSM. We train the TSM model on the instances from both fixed and egocentric views. Here we report the performance on these views separately. The poor performance on the egocentric views highlights the challenging nature of recognizing actions solely from the egocentric point of view. When we investigate the performance of individual camera views, we see that the overhead cameras V4 and V1 have the highest accuracy, while the side cameras V5 and V7 have the lowest. And in the egocentric setting, the top headset cameras E1 and E2 have the lowest accuracy since they do not fully capture the table. Like many recorded real-world datasets, our dataset also contains a natural long tail of actions. We have a total of 1,238 tail action classes. A separate tally reveals a significant gap between head and tail action accuracy for recognition, which demonstrates the need to develop few-shot action recognition methods. Hand poses are commonly available from AR or VR systems and are significantly more compact than video features and is also independent of the domain. Our experiments on pose-based recognition tries to investigate if 3D pose and motion can be used to assist today's video-based action recognition benchmarks. In our experiments, we use the state-of-the-art pose-based action recognition architectures. The model achieves an action accuracy of almost 29%. However, its performance is worse than the video-based TSM. The verb accuracy for pose-based recognition is higher than the video-based approach, but at the cost of object performance. This is unsurprising, as hand poses can easily encode movements but cannot provide much object information. Now, to assess the importance of objects, we add an oracle experiment by fusing the ground truth object information with the pose model. This results in a significant jump in action accuracy, which encourages us into exploring joint modeling of 3D objects and hand poses for action recognition. So, to summarize, Assembly101 includes multi-granular action segments to study goal-oriented sequence learning. Our dataset is designed to bridge video understanding and 3D geometry of hand-object interactions. We also introduced the task of mistake detection. The dataset has been made publicly available. We hope that the community will find other applications and tasks to benchmark on Assembly101. Thank you.